welcome to part 2 of sum and difference formulas for trigonometry. So we've got a list of formulas that I showed you in the previous section. You need to know all of these formulas. Again, a reminder for sine, it alternates. So it's sine of alpha, cosine of beta. Whatever operation stays cosine of alpha, sine of beta. Notice the order of the angles stays the same and the trig functions alternate. On the other hand, for cosine, the operation is opposite. If you have a plus here, you have a minus here, but the trig functions are cosine, cosine, sine, sine. And then tangent is almost like you use a distributive property, but that is definitely not what this is, because this is not multiplication, but it's tangent of alpha. Whatever operation goes on top, tangent of beta, and then one, change the operation, multiply the two trig functions together. So these are a need to know, unless you want to memorize how to do the proof, and then you could always reprove it to yourself, but you would have to do that for 4 different proofs. Now tangent of alpha and plus beta and tangent of alpha minus beta can be proven from these, and I think I have a problem in this lecture where I show you how to do that. But we're doing just a basic problem right now. We're trying to find the exact value of cosine of 15 degrees using the sum difference formulas. Okay? Now first of all, maybe let's write down the sum difference formula for the cosine of anything. Okay, so cosine of alpha, and it says difference formula, so let's say minus beta. Now, you have to go back to what I just told you. Do you have it memorized? Remember, cosine is cosine, cosine, sine, sine. So it's going to be cosine of the first angle, which is alpha, cosine of the second angle. Remember, this is just multiplication right here. Whatever operation is in your problem, which is a difference in this case, is going to be opposite. And then it's going to be sine of the first angle, which is alpha, times sine of the second angle, which is beta. So this is the formula we're supposed to use for this particular problem. But if you'll notice, we have another extra little issue going on. We don't have 2 angles. We just have 15 degrees. Now notice it says something also important, find the exact value. Now y'all know what finding the exact value actually means. It means don't use a calculator. Okay? So first of all, we need to come up with what 15 degrees is. You remember that's not on the unit circle. Using 2 values that are on the unit circle and subtracting. Okay, so how about we try the cosine of, now you think about it for a minute. What are 2 angles that we know are on the unit circle that we could subtract and get 15 degrees? Well, how about we do 45 degrees minus 30 degrees? That would work, right? That is 15 degrees. Did you have to do 45 and 30? No. There's other things you could do, like 60 and 45 would also give you 15 degrees. Am I right? And you could try it that way and see if you don't get the same answer I get. Because cosine of 15 degrees is cosine of 15 degrees. So let's plug this in our formula. Notice the first angle is 45, the second angle is 30. So this would give me cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. Now what? Well, we know these values on the unit circle. The cosine of 45 is the square root of 2 over 2. The cosine of 30, remember cosine is an x value, so the cosine of 30 is, remember, square root of 3 over 2. Plus the sine of 45 is also the square root of 2 over 2, and the sine of 30 is 1/2. So I simplify this. Square root of 2 times the square root of 3 is the square root of 6, and 2 times 2 is 4. You remember how to multiply fractions? Numerator times numerator, denominator times denominator. A square root times a square root. You can just multiply the values underneath and keep the square root. Here, square root of 2 times 1 is the square root of 2. 2 times 2 is 4. If you like, you can write this as the square root of 6 plus the square root of 2 over the common 4. And that will not simplify. Now, how do you know if that's right? How could you check yourself using your calculator? Notice we're not supposed to, because it says find the exact value, but how could we check ourselves? Well, the first thing you do is you get out your trusty calculator, make sure you're in degree mode, and find out what the cosine of 15 degrees is. Okay, so when I type that in my calculator, I have the cosine of 15 degrees, and I got 0.9659, and it continues on. I'm just going to take it out 4 decimal places. Then I could plug this in my trusty calculator. So I'm going to take the square root of 6. I'm going to add the square root of 2 to that, take that answer and divide it by 4, and I get 0.9659. Are they the same? Well, of course they are. That means we probably found this exact answer correct. Now, that's kind of defeating the purpose to use your calculator, but it is a nice way to check yourself. It makes you feel a little better about these problems if you check it with your calculator. All right, so we have another problem. Find the exact value of sine of 60 degrees plus 45 degrees. Now let's think about this. If we added these together, this would be the sine of, and that would be 105 degrees. Now is 105 degrees one of the values on your unit circle? And if you think about that, it's not. Okay, so that's why you can't just do this problem. You could type that in your calculator, of course, and find an approximate value, and we can do that at the end of this problem to check ourselves, but they want an exact value. So if you were given 105 degrees, you could write it as the sine of 60 plus 45, but they went ahead and did that for you. So the first thing we need is the formula. So we're doing a sum of sines. Now, you've got this memorized, right? Sine alternates, so it's sine, cosine, cosine, sine, and whatever operation is in your problem is the same operation in the formula. So you have sine of, I'm going to write it down, alpha plus beta is the sine of alpha, the cosine of beta, plus the cosine of alpha, sine of beta. Again, so the sine alternates. The last one we did was a cosine, and it doesn't alternate. It goes cosine, cosine, sine, sine. Okay? Whatever operation, you keep the same operation, where if it was a cosine problem here originally, it would be the opposite operation that you use. Now let's actually plug that in our formula. So we're looking for the sine of 60 degrees plus 45 degrees. That's going to be the sine of 60 degrees times the cosine of 45 degrees plus the cosine of 60 degrees times the sine of 45 degrees. Okay, so the sine of 60. So again, from your unit circle, that's the square root of 3 over 2. Remember, sine is a y value in the unit circle. Cosine of 45 is square root of 2 over 2. Plus the cosine of 60, that's the x value at 60 degrees, which is 1/2, times the sine of 45, which is the square root of 2 over 2. I simplify this expression. The square root of 3 times the square root of 2 is the square root of 6 over 4, plus 1 times the square root of 2 is square root of 2 over 4 is equal to the square root of 6 plus the square root of 2 over the common 4. Now, how could we check ourselves? Well, we could evaluate the sine of 105 degrees using your trusty calculator in degree mode. And I get 0.9659. Does that number look familiar to you? I plug this in my trusty calculator. So the square root of 6 plus the square root of 2. And then I find that answer and divide it by 4, 0.9659. That means that I probably did this problem correctly. Okay? Now, I'd like you to spend a minute and think about why this is exactly the same answer as the last problem that we did. Good question, huh? All right, next problem. I have a proof for you. So I want you to be able to prove that tangent of alpha minus beta is the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha times the tangent of beta. And to do this, we're supposed to use the sum difference formulas for sine and cosine. Okay, so maybe that's where we should start. Let's turn all this into sine and cosine. So I've got tangent of alpha minus beta. How about we say the left-hand side is equal to tangent of alpha minus beta. And we're really just verifying an identity here. We're not doing like the first proof we did and doing this geometrically. We're just verifying the identity. And we can rewrite tangent of alpha minus beta using the quotient rule. This is the sine of alpha minus beta divided by the cosine of alpha minus beta. Again, of our fundamental identities, that is the quotient identity. And then we will use our sum and difference formulas for sine and cosine. So remember, sine alternates. So this is sine of alpha, cosine of beta. You keep the same operation when you're dealing with sine, and you alternate. So now it's cosine of alpha, sine of beta, divided by, and I'm going to use the formula in the denominator as well, but the formula for cosine. Remember, cosine is cosine, cosine, change the operation, sine, sine. So it's going to be cosine of alpha, cosine of beta, plus, because this is a minus, and then I do sine of alpha times the sine of beta. What would I write there? Sum difference formulas. Okay, always have a line when you're verifying identities. Have a line, an explanation line for every line that you do of proof. Now we look at this and we think, oh my goodness, what do we have here? How am I supposed to turn all this into this? Does anything cancel? Well, as it stands right now, no. And this doesn't factor. There's no greatest common factor I can factor out of here. There's no cancellation that I can do here. But I can do a trick. Okay? And the trick is going to make pretty good sense. It's an attempt. We're going to multiply by something called a unity fraction. I know you've seen that before. A unity fraction is just a fraction equal to 1. All right? Now, look at this compared to what this is supposed to equal to. Somehow, there's a 1 right there. We've got to turn this term right here, probably this term, into a 1. This term, it appears, turns into a tangent of alpha and a tangent of beta. Now, to turn this into a tangent of alpha and a tangent of beta, it looks like I need to multiply or divide this by a cosine of alpha and a cosine of beta. That would work, right? If this was over cosine of alpha, that'd make that tangent of alpha. If this was over cosine of beta, that'd make that tangent of beta. Well, notice that's exactly what's sitting right here, cosine of alpha, cosine of beta. So we're going to do a crazy trick. We're going to multiply this entire expression by a unity fraction, and that unity fraction is, now let's rewrite what we have, sine of alpha, cosine of beta, plus, minus, my bad, minus cosine of alpha, sine of beta, over, I'm just recopying right now, so cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. Now for my unity fraction, I'm going to do this in a different color so it really stands out for you. This is going to be 1 over cosine of alpha, cosine of beta in the numerator, divided by 1 over cosine of alpha, cosine of beta in the denominator. Now that is a fancy unity fraction. You agree? So now I want to multiply these two together. So I have, this is equal to sine of alpha, cosine of beta, over cosine of alpha, cosine of beta. So notice I'm distributing. I'm doing this times this, then I'm going to do this times this. So that's minus cosine of alpha sine of beta over cosine of alpha cosine of beta. I know it's just a lot of writing. Divided by, now I'm going to do this denominator fraction times this first term. This is going to be cosine of alpha cosine of beta over the same thing, cosine of alpha cosine of beta, and then plus sine of alpha sine of beta over cosine of alpha cosine of beta. Okay, now, so what would I write for an explanation there? I just used the distributive property. I just multiplied my unity fraction times my expression that I've been working with, and that gives me, again, this fraction minus this fraction over this fraction and minus this fraction. Now we need to simplify. Now notice I've already gone through several of these steps, so I'm going to take a minute and erase, and we're going to pick up with this bottom line up here, okay? And I'll do that in a different color. So I've given us some room to get the job done. Now I'm looking at this first fraction, sine of alpha cosine of beta over cosine of alpha cosine of beta. Notice that the cosine of betas cancel. So I have sine of alpha over cosine of alpha minus, looking at this one, notice the cosine of alpha and the cosine of alpha, they're going to cancel, and I'm left with sine of beta over cosine of beta. All right, in the denominator, cosine of alphas cancel, and then cosine of betas cancel. All of that cancels, so I'm just left with 1. And then here, nothing cancels, so I'm going to put plus, and that's going to be sine of alpha sine of beta over cosine of alpha cosine of beta. And, you know, you just canceled common factors. That's the detailed way of saying it. If you just told me you canceled, I'd be fine with that. Now, sine of alpha over cosine of alpha. Notice you're using the same angle as your argument, which means that's just tangent of alpha. So we have tangent of alpha plus, similar thing here, they're both beta, and so I have sine of beta over cosine of beta. That's tangent of beta divided by 1 plus, now here I've got sine of alpha over cosine of alpha. That's tangent of alpha, and sine of beta over cosine of beta is tangent of beta, and that is multiplied together, and that's the end of our proof. And we used the fundamental identity for quotients. Okay, so we proved using the sum difference formulas for sine and cosine that tangent of alpha minus beta is equivalent to this right-hand side of the expression. Now the next problem you might run across is find the exact value of cosine of 50 degrees, cosine of 5 degrees, plus sine of 50 degrees, sine of 5 degrees. Now again, keywords here, we're supposed to find the exact value. You know what that means. It means absolutely no calculator. Okay? Well, y'all, 50 degrees and 5 degrees are not values on the unit circle. So I'm not going to just jump in and evaluate the cosine of 50 by going to my unit circle and the cosine of 5 by having my unit circle memorized. It's just not going to work. But on the other hand, maybe we can use the sum difference formulas in reverse to figure out what to do with this. First of all, what sum difference formula is this? So is it a sum difference formula at all? Do we have a sum difference formula that says cosine, cosine, sine, sine? And we do. That's got to be a cosine one, because remember the cosine one does not alternate. It goes cosine, cosine, sine, sine. And it is the cosine difference formula because it doesn't alternate, but the operation changes. So I know that this is going to be a minus, and then the first angle always goes in the first spot, and the second angle goes in the second spot. If you don't believe me, just look up the formulas. Matter of fact, we'll go back and look it up. So cosine, cosine, and then plus sine, sine. Let's look it up. So notice over here on the right, I have a cosine, cosine, and a plus sine, sine. And that formula is the cosine of alpha minus beta, which is the one that we use, so good deal. All right, now, do we know the cosine of 50 minus 5, which is 45 degrees? Well, sure we do. That is a value on the unit circle, and we know that answer is square root of 2 over 2, and that's all there is to that problem. So we are to find the exact value of tangent of 4 pi over 3 minus pi over 4. Okay, now are those values on the unit circle? Is 4 pi over 3 a value on the unit circle? The answer is yes. Is pi over 4 a value on the unit circle? The answer is yes. Is the tangent of 4 pi over 3 minus pi over 4, if we calculated this, is that a value on the unit circle? Possibly. We could check that out if you want to, but let's just use the formula first of all. So we need the tangent, the difference. You know this formula is going to be tangent of alpha minus tangent of beta over 1, whatever operations here changes, tangent of alpha times the tangent of beta. So the tangent of alpha would be the tangent of 4 pi over 3 minus the tangent of beta would be the tangent of pi over 4 over 1 plus the tangent of 4 pi over 3 times the tangent of pi over 4. And we just continue to simplify. So what is the tangent of 4 pi over 3? Remember, tangent is remember, first of all, where is 4 pi over 3? This is 3 pi over 3, so one more right here is 4 pi over 3. So the tangent's the y value over the x value, so this will be the square root of 3 over 2 divided by the x value is 1/2 minus, and the tangent of pi over 4, most people know that that's 1. In case you didn't, y value square root of 2 over 2 divided by x value square root of 2 over 2. Okay. And this is 1 plus the tangent of 4 pi over 3 is what it was the first time. If you wanted to go ahead and simplify that, and now most of you can see, you can go ahead and invert this 1/2 and multiply. That does just give you the square root of 3. And then invert and multiply, that's times 1, right? Or you could put it just as you had it there, and that value is there. So I continue to simplify, and the 2's cancel right here, so that gives me the square root of 3. Minus 1 over 1 plus the square root of 3. And that is your exact answer. That could probably be simplified. You could rationalize the denominator by multiplying 1 minus the square root of 3 over 1 minus the square root of 3. And it might simplify a great deal. The other way to do this problem, I mean, if it works, is go ahead and evaluate 4 pi over 3 minus pi over 4. Is that a value on the unit circle? Well, let's just try. So that'd be the tangent of, and we need a common denominator to pull this off. So I'm going to multiply the 4 pi over 3 times 4 over 4, and the pi over 4 times 3 over 3. So that would give me 16 pi over 12 minus 3 pi over 12, which would give you tangent of 13 pi over 12. That's not happening, folks, is it? That's not a value on the unit circle, so we couldn't reasonably do it that way. We had to do it this way to get an exact value for our expression. Now, I am okay with you leaving your result like this. I'm not going to request that you rationalize these denominators, although it can simplify sometimes a great deal, but I am okay with that particular answer. So I'd like to do one more problem in part 2 of our video. Now that makes for a long video, but find the exact value of tangent of pi over 6 plus 2 pi over 3. It's not tangent of each of them by any means. We need to use our formula, which says that to be tangent of alpha, keep the sign, plus tangent of beta over 1, whatever operations here, you do the opposite, tangent of alpha times tangent of beta. And I plug in my formula, so this is going to be tangent of pi over 6 plus tangent of 2 pi over 3 over 1 minus tangent of pi over 6 times the tangent of 2 pi over 3. Then you consult your unit circle. Y'all know where pi over 6 is. Tangent is the y value, which is 1/2, divided by the x value, which is square root of 3 over 2, plus the tangent of 2 pi over 3. Okay, you know where that is on the unit circle. The y value there is square root of 3 over 2, over the x value is 1/2, but the x value is negative, okay, divided by, this is going to be 1 minus. Now, tangent of pi over 6 we've already calculated right here. If you want to go ahead and invert that and multiply, you would get 1 over the square root of 3, because the 2's would cancel, times tangent of 2 pi over 3. Again, we've already calculated that here. You can flip that and multiply. The 2's cancel, but the negative doesn't. So that's negative square root of 3. I continue to simplify. I think I'm going to go to the right. When I invert and multiply, that's 1 over the square root of 3 minus, because of this, okay, square root of 3. If you want to put that over 1, you certainly can, over, these square root of 3's cancel. You notice that? And this negative times this negative is positive. So it's going to be 1 plus 1. All right, so now I've got to combine this together. So I need a common denominator. The best thing to do might be to go ahead and rationalize this. Okay, and then you would still, that's going to give you 3. You'd still have to multiply that by 3 over 3. You follow me? Because this is going to be the square root of 3 over 3, which means I'm going to need a 3 down here. So this is going to be minus 3 square root of 3 over 3 over 2. What a mess. So that equals 2. The square root of 3 minus 3 square root of 3 over that common 3 divided by 2. Well, square root of 3 minus 3 square root of 3 is minus 2 square root of 3 over 3. Now this is 2 over 1, right? So I flip that. That's going to be 1/2. The 2's end up canceling. So that's negative square root of 3 over 3. And to me, that looks like one of those regular old values on the unit circle. But how could you check yourself? Plug this in the calculator. Go in radian mode. Let's do that in red. In radian mode, I'm going to type in the tangent with parentheses of pi over 6 plus 2 pi over 3 and see what I get. When I type that in, I get negative 0.577 rounded 4. And when I type this in, I also get negative 0.5774. So that means my exact answer is correct. But also that makes me suspicious that if we went ahead and added this together, would that not be a value already on the unit circle? So it wasn't necessary to use this formula. Now that's your call. If you want to always check those, you certainly can. We could do that right now. I need a common denominator, so I'd have to multiply this guy by 2 over 2. So that would give me pi over 6 plus 4 pi over 6, which will give me 5 pi over 6. Is that a value on the unit circle? Sure it is, right there. And then you could do your y value, which is 1/2, divided by your x value, square root of 3 over 2. Flip it, that'll give you 1 over the square root of 3, which, what's negative? Oh, the x value down here. Okay, so that would make that negative, and that would give us exactly this answer when we rationalized it. Okay, so sometimes there's 2 ways to skin a cat. We got it though. Last one on the video.